This is the CFB fitted with the external heat exchanger diagram. In here we can see the external heat exchanger in the left side of the boiler, and fuel and air is input of the boiler in the bottom of the boiler, and it is the feed water is fed into the external heat exchanger, and cyclone separator is also there. The flue gas is going to the boiler from bottom to top, and from the cyclone the separates the unburned coal or some solid particles is again going to the bed through the pipes, through the external heat exchanger also. And superheater is also available in the top of the boiler, and the flue gas is going to the economizer, and feed water inlet is giving to the economizer, and it goes to the boiler drum. After the steam is goes to the superheater. So the flue gas then passes through the air preheater and going to the bottom. This is the circulating fluidized bed boiler. It has no EXE. Its superheater is placed in the dense phase flow. And here we can see the auxiliary gas fired burners, and primary air is inlet to the bed. It is the primary air is coming from the air heater. The fan is available in the bottom of the air heater. An ID fan also available in the outside of the air heater. First we can see the flue gas flow. The air is inlet to the boiler, and flue gas is flowing through preheater, superheater, evaporator, and it goes to cyclones to separate the solid particles. And after the flue gas is going to air heater, and from the ID fan it goes to stack. And the water circuit, we can see the boiler feed water pump in the left side of the boiler, top of the boiler, and feed water pump is pumping the water to evaporator, then it goes to the water wall panels, then it goes to the superheater, reheater, superheater. After then the superheater steam is going to the turbine. After the turbine the steam is going to the condenser, and the condenser, after the condenser the condensate extraction pumps are not shown, and the coal and limestone is given to the boiler in bottom of the boiler. There are in right side of the boiler we can see that tertiary air, secondary air, and fly ash removal and fly ash recirculation to fly ash silo, all we can see. So we can go to the page number 40. The question, first question: are the CFBs provided with soot blowers? Answer: though the requirements of soot blowing for CFBs are much less than for other solid fuels fired boilers, such units are provided with soot blowers. The next question: CFBs offer fuel diversity and cost reduction. What fuels do they burn, and how much cost effective are they? Answer: CFB, circulated fluidized bed boilers, burn vertically all types of low grade solid and solid waste fuels: municipal refuse, peat, industrial waste, coal water slurries, sewage sludge, petroleum coke, oil shale, coal mining waste, manure, wood, biomass. The degree of variation in these fuels is striking. Two existing natural gas fired boilers of large independent power cogeneration site in North America were revamped and replaced with two CFB units producing 100 megawatt of electricity each and 36 tons per hour of steam for process use. The units were brought into operation in 1992 and are designed to use 100% of petroleum coke. This coke comes from two local refineries who are recipients of some of the electricity generated by the plant. Switching the petroleum coke, reducing fuel cost by almost 90%, including the cost of limestone, fuel transportation, and ash disposal. Water treatment system, deaerator, condenser, boiler feed water preheaters, and boiler feed water pumps were all salvaged from the erstwhile utility units. And here we can see the comparison typical waste characteristics of some waste and alternative fuels fired in CFB boilers. The type waste coal source is bituminous coal mines in North America. Description: Actic 65% of ash, acidic 1.8% sulfur, 6 to 10.5% of moisture, 13,514 kg per kilogram. And culm, anthracic mining byproduct, high in ash content, high levels of potassium and halide, low heating value. Biomass. Biomass, agriculture waste, forestry byproducts, urban waste, etc. Leafy or green residual high alkali levels, grade size variability 10 to 60% of moisture, 6990 to 22,135 kilojoule per kilogram, blending necessary to maintain some consistency. Peat box 40 to 70% of moisture, 8,000 to 21,840 kilojoule per kilogram, 65 to 70% of voltage, 4 to 7% of ash. Petroleum coke, petroleum refining, high heating value, low volatile, high sulfur content diffusing to use in convection boilers. Lignite, more mines in Thailand. 25 to 50% of moisture, 7 to 35% of ash, and 8,400 to 13,020 kilojoule per kg, 0.9 to 3.2% of sulfur. So lignite is low calorific value, and we can see the biomass has high calorific value. So comparison of typical waste fuel analysis: component, bituminous coal waste, petroleum coke, 80% of coke plus 20% of TDF, anthracite coal waste, tire drive fuel, and fixed carbon percentage, volatile matter percentage, ash percentage, H2O, sulfur percentages are available in that comparison. Source: Electrical Power International, September 1994. Reproduction with kind, permission of Alstrom Pyrometer Incorporation, San Diego, USA. The question: the Pyrofro CFB boiler located at Cook Dong Oil Refinery in Sea Zone, Korea fires 100% of pet coal. Boiler performance has been excellent, easily meeting all performance guarantees. The boiler efficiency exceeds 90%. What is the reason of high boiler efficiency? This is primarily result of the low ash content and high combustion efficiency. The combustion efficiency has been greater than 98%. The next question: the Cookdong plant does not utilize fly ash reinjection. What would have been the outcome in this fly ash were reintroduced to CFP combustor? Answer: it would improve combustion efficiency even more. Again question: Cookdong plant. The Cookdong plant does not utilize fly ash reinjection. Would have been the outcome if the fly ash were reintroduced to the CFB combustor? It would improve combustion efficiency even more. Question: what are the advantages of petroleum coke combustion in CFB firing over more traditional firing? Answer: superior ignition and flame stability, excellent combustion efficiency in the range of 96 to 99.5%, low fuel emission without back and gas cleanup, NOx emissions are as low as 0.0215 to 0.0859 kg per mmkg without ammonia injection and less than 0.03 kg per mmkg with ammonia injection. Relative intensity to low melting vanadium components, ability to easy handle varying fuel equity, sulfur removal of 90% on greater by infernus lime injection. These are the advantages of petroleum coke combustion. Thank you.